So today I would like to present my paper, which titled 3D skeleton-based action recognition using LSTM network. So here's the outline of this paper. First, we're gonna do the introduction and the method, and finally the result, discussion, and the conclusion. Action recognition has drawn a lot of attention in the past few years. It has been developed for various applications such as video surveillance, human-machine interaction, and video analysis. With the development of depth sensors such as Microsoft Kinect and Intel Sense, RGBD and skeleton datasets has attracted a lot of attention. Compared to RGBD dataset, skeletons are more robust to noise and require much less computation with a low-dimensional representation. Recently, deep learning methods using skeleton sequences have been applied to human action recognition and achieve a good result. Furthermore, long short-term memory or LSTM network was exploited as a favorable solution for learning a human action recognition. It also used to model for time series data. So this LSTM network is actually learn the previous information. So the information from current skeleton sequences and the previous skeleton sequences are combined with the memorized knowledge to provide an action label at each timestamp. This research is not using the primary data, but the existing dataset, which is NTU-RGBD dataset, which is the large-scale benchmark dataset for 3D human action recognition. It actually consists for about 100,000 RGBD video data captured from 106 distinct human subjects. And there are two evaluation benchmarks that are used. First is the cross setup and the second is the cross subject. Next, we're gonna through the methods. The methods are divided into two parts. The first part is the data pre-processing and the second part is the network modeling. Before we going through the data pre-processing, first I would like to explain a little bit about the dataset that we use. We use the NTU-RGBD 120 dataset. It's the newest and the largest dataset in the human action recognition. It's actually, there are 120 action labels. So this dataset is collected by Microsoft Kinect sensors and actually has four major data modalities. First is RGB frames, second one is the infrared frames, depth maps, and the last one that we use is the skeleton data. As you can see here, there are examples of the RGB videos, the infrared videos, and the depth maps images. And here are the steps that we use in the data pre-processing. First, we convert all the raw skeleton data to math files and save only 3D coordinates XYZ information using MATLAB. So actually, skeleton data consists of 11 data, but we only use the last three coordinates XYZ using MATLAB. Among 100,000 dataset, we divide it into two categories, for training data and for testing data. And we also have another categories for cross setup and cross subject. So for cross setup, we divided the data to different camera setup, and for the cross subject, we divided by their subjects. Next, we're gonna take a look at the network architecture. As I said earlier, we use the long short-term memory network or architecture that we use to construct the model. So LSTM is employed to construct the network with two different architecture compared to the validation process. We have two LSTM model. The first one is we only use one layer, following by a fully connected layer, and the second one is the two-layer LSTM following by fully connected layer. Another parameter that we use are the hidden unit of LSTM layer is the 256, and the hidden unit of fully connected network is 128. We also use the softmax classifier with 120 action labels, and each layer has a dropout layer with weight 0.5. And the last calculation that we use is the categorical cross entropy loss with the Adam optimizer, and we training it with 50 epochs. The network is implemented by TensorFlow on the workstation with an NVIDIA GeForce GTX 1080. So here are the results. For one layer LSTM, we got 45% for cross setup accuracy and 38% for cross subject accuracy. And for two-layer LSTM accuracy results, we have 43% for training accuracy in cross setup and 46% training accuracy in cross subject. For more easy understanding, here are the graph of the results. We can see here that the result accuracy is increasing from 0 epoch to 50 epochs, but the testing accuracy is always below the training accuracy. So what we can conclude are the training and testing accuracy for both networks are still very low, which is less than 50%, and the cross subject has better results than cross setup in both networks. And the two-layer LSTM network has better results than one-layer LSTM network. While low accuracy can actually caused by many factors. For example, because this dataset that we use is a very large dataset, it has up to 9 million frames and has too many noisy skeletons, or maybe there's something wrong with our pre-processing data. We also can try to change the neural network and tuning the parameters in our neural network. For example, we can change the hidden unit, the learning rate, weight decay, dropout, regularizers, epoch, and so on. So I hope we can tuning more parameters and get better results for future work. So at last, I want to say thank you for watching, and I apologize for any mistake that I made, and I hope this research will be useful for any future work. Thank you.